I am doing lecture number 8 and I am going a little slow also. Okay, I am going slow from a section A and B, but still you are lagging behind. I don't know. Section A and B का quiz हो चुका है? Anyone has an idea on this one? आज है? They are little late, but anyway. Okay, ji. So this is lecture number 8, chapter number 7 of your Chapman over here. And as I have told you on this one, that after your magnetic circuits, today we are discussing the DC machine over here. And over here I have this stator and rotor. This is a not purely a DC machine, but this is actually a vacuum cleaner machine over here with me. A good design machine. I don't know which side it's burned or not. This is the stator side and this one is the rotor side with me. I will just pass it on to you also. So this machine over here, which is in my hand, is actually a vacuum cleaner machine, and it came from US. It was 110 volt rated over there. Now because of 110 volt rated, actually my mom plugged it in at 220 and it got burned. So now I have made it as a test mule or something like that. So this is the stator in my hand. I will just show you on this one also. I'm passing this one to everyone, and today we are discussing this whole your stator and the rotor part. And you can see over there the rotor, it can be turning on. You have the carbon brushes over there. Please don't try to pull this off otherwise, because this is not going to be taken out over there. So this is still working, and the two terminals of the carbon brushes are this wire and this one over there. So this actually goes on inside this rotor or stator over here, and this is actually the working, and from here the actual suction and all that thing happens. Now this machine is actually a motor from your vacuum cleaner. The only reason for this one is this: is you have started your lab also. In your lab you have a series motor. You have done experiment, or maybe you have been shown. Now series motor, the field winding and the armature winding, they both are in series. So this motor is applicable for voltage AC also. Why? Because in AC we all know it's changing positive, negative, positive, negative. So when it's changing, both windings are having a direction current change. So what happens? The torque which is being produced by this shaft remains unidirectional. Otherwise, if you want to reverse the direction of a DC machine, what you have to do, either you have to change the field winding current, these two poles over there, you can see the two poles over there, and or either to change the direction of this one. But in my hand, this is actually a series motor, and this series motor is a universal motor because it can run at AC also. Yes, certainly there will be a difference of some output parameters, because when you are having AC, inductance comes into play, but when you have a DC supply, then inductance does not come into play, because you are aware of this one, that at DC, inductor behaves as a short circuit. So this machine, which is called as a universal machine also, because it can run at AC and DC. And I guess in the lab it has also been told to you that your series motor or universal motor, whatever you call it, these both machines are having a very high torque. And that's why this is also the same machine used in your juicers, blenders, vacuum cleaners, drill machines, wherever there is a very high demand of torque over there. Now, when times if you have seen a juicer or blender over there and you have some crushing the nuts or something like that, the only power that you're actually getting it from those blades. But this motor has a very high starting torque. I will decide on this one when we talk on this one, that why this is a very high torque at that time. But over here, this machine is a part of your juicers, blenders, vacuum cleaners, drilling machines, or any other which are having a requirement of high torque over there. High torque, I mean that it has a huge load on it. So this is a machine over there. I am passing this one over here in the class. Please kindly everyone have a look. Meanwhile, I am talking about this machine over here in your lecture. Now, in your lecture number 1, if you remember, we talked about this DC machine, and there was one loop over there. That one loop was actually a current carrying conductor or a coil. Now the word loop or coil, it's interchangeably used over there. So I am going to use the word of coil or loop. Now technically we call it as morely as a coil over there, because the coil is actually shown over here in this direction. So if I draw this one, this coil or loop is over here like this. So this coil or loop is, you can see over here I have marked it as A, B, C and D over there. So this ABCD loop is over there, and it is placed between a magnetic field. There is a north and south pole over there, as you can see over there. So this north and south pole, you have a north pole here, you have a south pole here. So this means certainly that a flux lines are flowing from the north towards the south over here in this direction. Now, since I am talking about a current carrying conductor placed in a magnetic field, this means I will have to apply my right hand rule. Now, if you apply your right hand rule and use your left hand, this finger is pointing out the direction of the magnetic field. This is the direction of the current which is flowing inside the conductor. This thumb points out in the direction of the force produced over there. So if you apply this one on your hand over there, if I'm doing this on my hand, so I have something like this. So over here, the direction of the current, if I want to mark it, let me have a markation on the current direction. So if this is the current direction flowing inside, so in this loop it is going like this, then in BC it's going like this, and then from CD it's coming out. So now if I apply this left hand rule on this diagram, I have north over here. I'm doing this one on my this one, so you can apply this one yourself over there. So this is my B for here, 9 to south, and the current is going inward of the board in segment number AB. So this means I have something like this over there on my diagram. But if I want to actually show on this one over here, so I have this one as north and south. So I have this one as B over here, and here the direction the current is going in. So this will be like this. So this is going inward, this is your B direction, so the force exerted is downward. So this means that on the segment AB over here, so if I draw this one on segment AB, I have the force exerted over here in this direction. And if I go in a little bit direction over there, you all are familiar that we have the formula of F is equal to I into L cross B over there. Let me use another color. So if I have this one and this one, so we know F is equal to I dot L cross B. So I have this one F over here. So this F over here is the IL cross B. Now L cross B over here is the vector product over there, which is actually having a dot product with the I over there. So this is IL over B. So L cross B over here is being having. Now in this segment over here, AB, I'm talking about this segment AB over here. So in segment number AB, the force F is produced in the downward direction. The force produced in segment BC will be 0. जी कोई बताएगा क्यों? Which angle is 90? Current and magnetism. The current is flowing in this direction, the B is flowing in this direction. So the angle between them is either 0 or 180 degrees. It can be 0 when it is going to be flowing in this DA segment. Otherwise, when I'm talking about BC, it's going to be anti-parallel over here. So the two segments which are going to have a power produced inside them, the force produced inside them, are these two segments, which is AB and CD over there. So when AB and CD are producing two forces, they are completely equal to each other. Why? Because the same amount of value of current is flowing over there. So these two forces are going to make a couple of force, and you are going to have a magnetic rotation over there, and that rotation is going to actually give rise to some circular motion over there. So this means that according to this direction over here, your machine is going to move in clockwise or anti-clockwise. This is clockwise. Okay, so this is moving clockwise over there, board over there. So this is a clockwise rotation over there. Now after 180 degree of rotation, I told you in the first lecture also, you can go through it again, that there is certainly going to be a carbon brush over there, and that carbon brush is actually going to be connected with a commutator segment, and that commutator segment is just going to be called, in our case over here, I am showing this one as two carbon brushes. So over here, these two red colored carbon brushes, they are actually going to have the current flowing path given over here. So after 180 degree of rotation, the direction of the current path is going to change, and then afterwards, previously this was current running back, then afterwards when they return it, the loop direction of current will reverse, because we want the motor to, if it's moving in the clockwise, it should remain in the clockwise direction. Otherwise, if we don't reverse the direction of current, then what will happen? It will move like this and then come back, move like this, then come back. So it's not going to be a unidirectional motion. So the commutator over here, and what is the commutator over here? Commutator is this black color over here in 3-dimensional. But if I want to actually show this one over here it is actually in 2-dimensional, is actually the circle and another circle over here. And so this is actually a ring which is split into 2 halves. So this ring has been split into 2 halves, and there is a carbon brush added over here, and this carbon brush is in contact with this one over here. Now the machine which is coming towards you and you are seeing it, it has just not only 2 commutator segments over there. This one over here is a commutator segment over here. This one, sorry, red color, I have to use blue color. So this is a commutator, and practically the machine which is in your hand, it is also having a commutator, but it is not having only 2 segments, it is having more than 2 segments. What I mean by this over here, if I draw, supposingly, let me draw it somewhere here. So if I have this ring over there, and inside this ring, what I am going to do, so in this ring over here, supposingly, if I rub my, now in this diagram over here, you can see how many segments I have made. 4 segments. Now what does 4 segments mean? 4 segments mean that now I am going to have 2 loops. So this one and this one, maybe one loop is going to be connected. This one and this one, another loop is going to be connected. So more the number of loops or coils, more are going to be the commutator segments over there. So the one which you are holding, I don't know, I have not counted it over there, but I guess there are like 20 or 21 or 22 segments over there. So those 22 segments are actually joining the number of loops. So what they have done actually, now here in this machine, there is only one way that you are actually going to have 1 loops or 2 loops or 3 loops or whatever number of loops, you are increasing the amount of force being produced. So each loop, but coming back to our loop discussion over there, because I will go afterward. So this loop A, B, C, D over here, the first loop is over here, FAB, force over here, then FBC is 0 for, and FCD is equal to ILB. So, and the last one is FDA over equal to. So I have these 2 values over here. If I want to find out the total force by 1 loop, that total force of 1 loop is going to be equal to 2ILB over here. And this FILB, now I want to find out the torque over there. So torque is certainly going to be equal to R cross F. For those who still don't remember it, R is the moment arm, F is the force over there. So when you have a cylinder in front of you, this is the cylinder over here, just like you have the rotor in front of you. So even if you have like just one loop over there, let me make one loop over there. One loop end is here, one loop end is here. So this is a cross-sectional view in front of you. So this is one loop, 2 ends. So this is the moment arm. So this R is actually the radius of that cylinder, or the rotor you can call it. So this R cross F, and since every time R cross F, it's going to be 90 degrees because of certainly the tension force. So this RF is always going to be 2RILB, where this angle theta is always going to be 90. Okay? So you are going to always get RF sine 90. So you are always going to have 2RILB. Now what is this one? This torque is actually the torque of 1 loop. Now I just told you that to increase the torque, you are going to have more number of loops arranged, and those connections are going to be done with how many number of segments you have over there. Plus there will be some series of parallel connections of the loops also, which we will discuss later on. Now at present over here, I am more concerned with this one. I am only concerned with 1 loop. Now if you see this 1 loop over there, in this 1 loop, you have a north pole and then you have a south pole over there, and flux lines are entering the cylinder from half of it and then leaving from the other half of it. So what I mean by over here, this portion, if I draw the cylinder over here, this portion, that is the half side, plus this portion over here, this portion over here is having the north side giving the flux, and then from this portion over here like this, it's entering the south pole. So if I show you a little diagram over here, if I give you the practical cross-sectional view like this over there, you have the flux lines entering from the north pole. So all the flux lines, they are entering from the north pole over here, and they are leaving through the south pole. So what is happening over there? If this cylinder is being now depicted in a 3-dimensional picture like this one. So what this means over there, half of that cylinder, which means this distance over here, and the other direction, which is not shown over here because it's three-dimensional. So all this portion over here is in front of the North Pole, and this half other portion is in front of the South Pole. Now I am talking about a machine with two poles and only one loop. So what happens over here, if I am seeing this diagram again, this means that from the North Pole, my flux is entering, and in front of the South Pole, the flux is leaving. So over here, through the cylinder, how much flux is flowing, I need to calculate that. For this purpose, if I want to find out how much flux is flowing, I need have phi p over here. This is the flux per pole. Phi p is flux per pole. So phi p is equal to BAP. What is B? B is the flux density. AP is the area on which that flux density is incident. Now what is that area? This is very important. AP here stands for the area under one pole. So if you are seeing this cylinder over here, if it is a two-pole machine, this distance over here, this one, is in front of one pole. The remaining half is in front of the South Pole. So when I want to find out the surface area of this cylinder, I will have to actually find out first of all the circumference, which is 2 pi r, because r is the radius of the cylinder. So this is 2 pi r, and this cylinder is actually having a conductor inside it, certainly. At present only one loop. I'm not talking about more than one loop. So the length is L. Just like you had the formula for F is equal to ILB. What was L? L was the length of the conductor placed in the magnetic field. So this cylinder over here, this is going to have a surface area of the cylinder equal to, so the surface area of the cylinder is going to be equal to 2 pi r L over here. Agreed on this one? Okay, 2 pi r is the circumference, L is the length. So this is the surface area, total surface area. Now in my case, I have only two poles. So this means when I am trying to find out the surface area under one pole, AP, this will be equal to AS divided by 2. Because I have two poles over there. Now, generically, if I want to only have a generic formula, this will be equal to AS divided by P, where P is the number of poles. So it can have 4 poles, it can have 6 poles. Remember one thing, number of poles are always an even quantity. It's always going to be even quantity. You cannot ever have, just like you can't have a positive charge without a negative charge, similarly, any pole cannot exist in singleton. It always has to have north, it's always going to have a south pole. So over here, what is AP over here? AP is equal to AS divided by P, and AS is the surface area of the cylinder on which the whole flux is coming in or coming out. So AP is that portion over here. So now, if I know my torque is equal to 2RILB over here, so now I am more interested in this torque over there. So I know torque over here is equal to 2RILB. And from the previous relation over here, I know that my AP over here, if I just let me just do a little addition over here. Okay, so I know, I'm doing this one again, so you can follow this one. So my total torque was 2RILB. We have just done it. And I have just found out that my surface area per pole is equal to AS divided by P, or in my case, P is equal to 2. And if I put down the equation over here, this is going to be 2 pi RL divided by P over here. This is the surface area. And I know what is flux phi. Flux phi is equal to B dot AP, and flux phi, certainly P you can add it. Some books they don't do it. Flux already is taken as flux per pole. So this is going to be B multiplied by 2 pi RL divided by P. Now you have your phi P over here equal to B into 2 pi RL divided by P. Now from this relation, you can take out your value of B. Now, when you take out the value of P, this will become as phi P into P divided by 2 pi RL. So your B is equal to this form. Now you can take this B value and put in this torque formula. So what happens, your torque total for one loop, it comes out to be 2RIL multiplied by this value of phi P into P divided by 2 pi RL. So over here, some things are cancelled, 2 and 2 are cancelled, L and L are cancelled, R and R are cancelled. So what I have now over here, your torque total is equal to phi P into P divided into I divided by pi. So this is your torque equation over here. Now, this is a generic equation because here number of poles of P is equal to just P. I have not put any T value. So if I have a case where number of poles are equal to 2, so this total torque for a 2-pole machine becomes equal to 2 by pi multiplied by flux per pole multiplied by the current I. And what this formula is telling you, this formula is easily telling you over here that 2 by pi, what is? It's a numerical constant. What is phi p? The flux per pole. So if you are going to have more flux per pole, you are going to have more torque. Similarly, you have more current I flowing inside the winding, you have more torque. So for a single pole machine, the formula is equal to torque equal to some machine constant or some numerical constant. Here in this case, this is 2 by pi. Then you have flux phi p and I. And these two parameters, flux phi p and I, you can easily change them inside your machine. If you are using permanent magnets, get a hold of very good permanent magnets, your flux will increase. If you are using supposedly an electromagnet, increase the amount of field current. So now you are going to have more flux. Secondly, the current which is flowing inside and coming out of it, increase it. Certainly, you can increase it up till beyond a certain level because you cannot go beyond the capacity of that wire. So there are two ways over here. So the torque is equal to 2 by pi into flux phi. You can write only flux. This is equal to 2 by pi into flux phi into I. So this is the formula for your torque for one loop. Now, we will just derive another in the next lecture. Most probably I will derive it for a complete machine also, where instead of just one loop, there are many loops over there. Okay? But before that, we move on forward. Now the next thing is this, that if there is a generator over there, because any machine, I told you in the very start, can work as a generator also if it is a motor. So you can interchangeably change their working over there or whatever. So now in a generator, we know E is equal to V cross B dot L. V cross B over here is a vector product having a dot product with L. L is the length over there. You're already familiar from this equation in your physics. So now E is equal to VBL, V cross B. Now if I go back on my diagram and now treat it as a generator. Now when I have a generator, please always apply right hand rule. For right hand rule over here. So if you apply this one on this diagram for segment AB. Now this F vector, this time it's not going to be the F vector. This is telling you that the velocity vector on this one is moving in this direction because you are trying to move it. You are applying a mechanical energy which is trying to move it, and you are going to get an electrical energy as an output. But we still don't know what is the direction of that electrical energy, which means the current getting out. So what you are going to get, if this is the V velocity vector, you can apply your right hand rule over there, do it yourself. I'm not going to show it to you. So E is equal to V cross B dot L. You are going to get an EMF induced, and that EMF is going to be induced in such a way that you are going to supposedly get a positive side over here and a negative side over here. But if you see this segment over here, BC, in BC there is not going to be any EMF induced for normal reason, because V cross B, here V is not direction, B is having a direction from north to south. So B is not having any direction over here. So in this portion, you are not going to have any EMF induced over there. Similarly, no EMF induced in this section. So when you are going to have the combined effect of this, this is plus, this is negative, this will be plus, this will be negative. So what you are going to get, you are going to get a total EMF from only two sides of your loop. And if I show this one over here, your EAB is going to be equal to VBL. ECD is going to be VBL, the rest two are 0. So the total EMF induced in one loop is going to be equal to 2 VBL over here. And since I know from your physics over there that V is equal to R omega, I hope you still remember omega. Omega was the angular speed of your machine in radians per second. So R is the radius, omega over there. So if I put this one in this relation, I get 2R omega BL. Now similarly, in this equation, this is the EMF induced over there, 2R omega BL. Now in this equation, again, B is there. I don't want to use this B. So what I will do the same thing just like I did in the torque equation. I will take out the value of B, put it inside this relation over there. And now over here, if I put in this equation and I have some cancelling done, so I have E total equal to phi by P divided by pi into omega into P. So this is a similar equation with having almost similar constants. How? This is P by pi. So if you remember your last equation, I just did it over there. This was 2 by pi or P by pi. Same thing. Then the other two things, here it was current I and flux. This time now it is equal to omega and phi P. So flux is always there. So flux is always a parameter. And omega is there. Omega is actually the input. In a generator, what is the input? Mechanical energy. So you get an electrical energy. So here in this, omega is the parameter over there. So you have more speed, you have more EMF out of the generator. Plus, if you have a better poles, if you have permanent magnets, phi P is going to be better. So you are going to get better EMF out from your loop over there. So this means that your E total over here, if it's for a two pole, you can easily find out that your E total is proportional to your flux and it is also proportional to your speed. So more the speed, more is the output. Similarly, more the flux, either from a permanent magnet or either from the electromagnet, you are going to have more EMF out of it. So the two equations over here, if I just read out down over here, this means that your E of, for a two-pole machine, your torque is going to be equal to 2 by pi into flux into I. And for your EMF for a generator, certainly this is for a motor and this is for a generator. So this is equal to 2 by pi into flux phi into omega. So these two equations are only for a single loop machine. This is very much important. Single loop machine. I only have just one loop. But I told you in the very start also that if you have a machine and you want to increase its output, you will have more loops placed inside the whole 360-degree periphery. This loop is arranged only just over here in one plane. Now you are going to arrange them. Larger the number of loops, more difficult is going to be the interconnection series or parallel. That will actually classify it as a winding over there. And that winding is going to be connected through your commutator segments. And the number of segments, which means that a whole ring is cut into how many segments depends upon how many coils you have. So similarly, if you have seen this one, you can see over there, please count this number of segments over there. Either count karo, so these segments, so these segments over here are the commutator segments, and these segments are going to take the energy from the carbon brushes, and from the next carbon brush they are going to come out. So these commutator segments, how many loops are there, they are decided when you are designing a machine. Now, another way of increasing the number of output or the amount of torque is this. Over here, what I did, I had a loop. This was going like this from here to here and then coming out. This is one single loop. Only this loop has only one turn, which means I took a wire going like this and completed it over there. Now, instead of doing this, what I do, I go like this, complete one loop, and I don't finish it off. I repeat it again. Now, this time there are 2 turns per loop. And if I want to make it 3, supposingly, let me make it 3. So this will be 1, 2, 3, and like this one now. So I have now 3 turns. Now, what will happen? Now I have 3 turns per loop. Each one is going to have a force F. So you are going to have more torque being produced. So this is another way. Now instead of just increasing the loops, you are now increasing the number of turns per loop or coil. So you are going to have more torque being produced over there. So if I go back over here on this one, this, if you see very closely this one, this diagram, north and south. Over here I have not shown any loop over there. But if I show this one with supposingly my first loop, let me use this one. This is my first loop over here. This is a cross-sectional view in front of you. Now this loop is having a flux flowing from the north pole towards the south pole. Now this loop is arranged parallel to your north or south pole. It will have turning effect over there. If it's a motor, if it's a generator, EMF will be induced over there. Now I want to increase the amount of EMF or whatever. So what I will do, I will have another loop supposingly placed here, then maybe another loop here, then maybe another loop here, then maybe another loop here, and then maybe another loop here, then maybe another loop here, another loop here, and maybe another loop here. So how many loops I have arranged over here, if I just make a small list over there. So this is one loop, this is second loop, this is third loop, this is fourth loop, this is fifth loop, and this is sixth loop. So now all 6 loops, they are arranged in the whole 360 degrees, which means approximately 12 ends are there. And since this is the whole 360 degrees, so this angle between them is approximately 30 degrees. Okay? For obvious reason, 360 divided by 12 over there, so I have 30 degrees over there. Now the question over here is it, which is very, very important. Listen to this very carefully. If you have seen this north and south pole, this shape of the north and south pole is curved. And if I compare this one with this one, here the pole shape is not curved. Now what will be the advantage of this one? If you see this diagram over here, which is having a perpendicular cross section over here, flux lines which are close over here, this air gap is small, flux will be more over here. But if the flux lines, they have to flow through air, this distance is more. So the value of flux over here will be small. Similarly, here it will be a little larger, but still small. The maximum would be at this point. So when I'm going to place a conductor over here at, let me use this one. So if I'm going to have a conductor over here and a conductor over here, and then there is another conductor over here, another conductor over here, another conductor. So the blue ones are not going to have the same EMF because flux is going to be small. And for another reason, because we know E is equal to V cross B dot L. Now here in this direction, B is coming at a different angle. On this one, it's coming at a different angle. So this V cross B, E is equal to V cross B dot L. This V cross B is not going to be the maximum. It's going to have a little different angle. So different value. So having this perpendicular cross section makes the conductors over here, this one at maximum, this one a little less, this one a little less, and this one almost zero. It's not going to have any EMF almost. So this north and south pole configuration as compared to this one. Now what is happening over there? By making the pole faces curved, now flux lines are going to go perpendicular out from here, perpendicular out from here, perpendicular out, and similarly like this. So when this will be perpendicularly coming out, E is equal to V cross B dot L. This value of V cross B is going to be maximum. So you are going to get an ideal voltage coming out from your waveform. Now if you see this diagram over here, now if I have, supposingly, let me just give you an idea on this one. If you see this red color waveform or red color loop over here, this red color loop, if it completes one complete revolution from here and then completes its revolution from here, and I want to plot the waveform of this red color loop over there, let me call it A, this is B. Certainly C and D will be at the back end. I can't show them because it's a cross-sectional view. So A and B loop over here, they are going to get an EMF induced inside them. For one complete revolution, the waveform will be something like this. Why sinusoidal? Because at this point, it's going to be maximum. Then it will start decreasing down and it will become zero over here at this point. And then it will again start increasing and become maximum over here. And this pole EMF is going to be produced. So the sinusoidal or approximately sinusoidal waveform is going to be produced over there. Now, over here, if I place another loop over there, now see this very carefully. If I place another loop over here at this point, and the other end of this loop is here, and let me call it supposedly CD. Now this loop is also going to produce a sine wave like this one over there, but it will be phase displaced, which means that when I'm going to place this one, it's going to be a waveform like this. Why? Because this angle A and C, they have a phase angle between them. So this angle is also going to be depicted over here by this angle over there. Now, if I place, let me just place another loop over there. Maybe I have placed another loop over here, and another loop. Let me call it supposedly E and F over there. So now the waveform on this one will be again more displaced like this. Like this. So this one was for AB, this one was for CD, this one was for EF. Now, if you arrange your whole periphery with different loops here, everyone, so all these loops are going to be connected to the commutator segment over there, and it's going to give an output. Now this is a DC machine. It's a DC machine output. So how this sine wave is there, how you are going to convert it into over there? So what you are going to do over there, this whole waveform is going to be rectified because of the commutator segment. So this green color waveform, yellow color waveform will be now like this, and this will be rectified over there like this. The blue color one is also going to be rectified over there, and it's going to be like this. Similarly, it's going to be rectified like this. And then the green color one, if I show it over here like this is going to be rectified over here like this, and this is going to be rectified over here like this, and certainly it's going to have some portion over here like this. So this lower portion is not there now. Okay, I'm not rubbing it for obvious reasons, so I'm not rubbing. So now what you have over there, you only have the topmost part. And if you see very closely over there, if I follow this trajectory like this is a DC with ripples. It's still a DC, so you will have to attach a capacitor so that it is almost a constant DC. So this is the disadvantage of having the pole shape in this direction. So you are getting ripples inside your output waveform. Yes, certainly your ripples will be reduced if you have more loops, but ripples still will be there, because more number of loop means that you are increasing this angle of decreasing this angle of 30 degrees. But if I go back on this diagram over there, what is happening over here, if I take even this loop and it is completing its whole 360 degrees over there, when it is in front of the north pole, it's having the maximum value of flux. So the EMF that is going to be induced is going to be maximum. Only for a very small portion here and here, it will be zero. Because at this portion there is no north pole, no south pole. So the waveform we are going to get output is going to be something like this. You can see over here what is happening. It remains high for a very long time, and then it goes for a zero, and then it goes in the negative, and then it's following this trajectory over here. More like a trapezoidal waveform. And in this same diagram, if I'm talking about supposingly this is the red color waveform. So if I have this one, supposingly this one is A, B. So if I call this one as A, this one as B, and I change this supposingly to C, and this is D. So now if I'm drawing now a CD waveform on this one, this will be similarly phase displaced. And this will be like this. So this is going to be CD loop. You add another loop, you will get another waveform. So, but at the end of the whole story is this, that when you are going to rectify it by the commutator, your waveform is going to be smooth. It's going to be a constant DC output. You may even not require a capacitor. So the shape of the pole, the bottom line is, the shape of the pole actually decides the shape of the waveform that is being induced inside your machine. Here you have made it curved. So the value of flux from this point to this point is almost constant. The only region is this one and this one where there is a transition. Okay? You can reduce it, but you can't make it effectively zero. So you are always going to have a transition from this point to the negative. You can maybe reduce this time over here, this time over here. This can be reduced, but overall it can't be made zero. You're always going to have, maybe your waveform is something like this, a complete square waveform. But complete square waveform has some other problems, because what you are doing, you are changing the direction of voltage or current every time. So it will have some inductance effect over there, LDI by dt. I hope you remember this thing. in an inductor, because what is happening, this winding inside it over there has an inductance, and if you change abruptly any value of current flowing through it, you are going to have a problem. There is going to be an EMF induced, there are going to be spikes produced over there, so LDI by dt effect will kick in. So this gap over here, this one and this one is a requirement also over here. So increasing the number of loops, you get a constant DC voltage out, because the commutator is actually rectifying it automatically, and you are getting an output. So the most preferred design is this one. Normally you won't see something like this. If it's like something, a very immature design or something, maybe you will get something like this. So even in this one, you can see the shape of the pole is curved. It could have been straight also, but then the output would not have been over there. So in your shape of your pole, that decides over here. And overall in this one, how many commutator segment? कितने? आपने निकाल दिया इसमें से, ये निकाला क्यों है? तो निकालना नहीं होता इसमें से. खैर इसको मैं बाद में देखता हूँ. How many 30? 25. नहीं 25 नहीं हो सकता. It can't be an odd number. It always, because every coil has two ends. Okay? It always has to be an even number, something like that. Now there are some series connections or parallel connections which I will not be talking very much detail today, maybe in next lecture. So this commutator segment may be like 30, 32, 36, whatever. The carbon brushes are going to be constantly in contact with this one. Now you can see over here in this hole, if I count this one over here, let me count it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 slots. And what I mean by slots, if I go back on this diagram, you can see in this diagram, how many slots are there? 16 slots I have made. What are slots? This is the slot opening over here. This is a slot opening over here. This is a slot opening over here. This is a slot. And what does it in this slot? In these slots, you are going to put your conductors over here. If you have only one coil over there, and that coil has only one turn, here practically it's not going to be just one turn, it is going to be more than that. If you count them and open it, it will be something 20, 30 or something. Here in this diagram I have only shown one. Why? Because the direction of current is either going to be a cross or it's going to be a dot. Okay? Cross going inward, dot coming out. So in this diagram you can see two poles which are maybe electromagnet or maybe permanent magnet, and here 16 slots are there, and each slot has an opening where you are actually going to put that conductor over there, and these 16 slots, there are going to be 8 coils. Now if there are going to be 8 coils arranged over here, how those 8 coils are going to be joined together, that depends upon the type of winding. But the common point is this, that all these, in this practical case I have only 12 slots, this means 6 coils are there. Now those 6 coils are going to be series, parallel, whatever connection that is done in the very start over there. But the point is that if these 16 slots in this diagram, each slot is being covered by one coil, then the number of layers of the winding is equal to 1. एक slot के अंदर you have only one layer over there or one coil, then this means it's L is equal to 1. But if you have two conductors of two different coils, what I mean by this, listen this carefully. I have a coil between slot number 1 and slot number 9. लगा दी, उसको मैंने 20-21 फर्स्ट को टर्न्स पर coil भी कर दिए. But I want to make another coil between 1 and supposedly 7. This means that slot number 1 has two coils, two different coils. Okay? So this means that my number of layers now will be equal to 2. 1 or 9 के दरमियान में you will start from 1, end at 9, and maybe make it like 10, 20, 30, whatever number of turns. Completely done. Then you have another coil from maybe 1 to 7, a different one. Then this means that slot number 1 or any other slot, it has to be number of layers equal to 2. Which is something like this, that you are going to have a double layer winding. Here this is a single layer winding. Normally I guess this in this one it's a double layer, I guess, most probably. Yeah, it's a double layer. How you can actually see this one? If you see very closely, a bunch of wires. In each slot, there are two bunch of wires coming in. You can closely see one is going in from one another slot, one is going to another slot. So this means maybe in this diagram, from 1 it's going to 12. This is one loop coming up like this. And then at the same time from 1 to 6, it's completing its path many different times. So slot number 1 over here has two different coils, and those two different coils make the winding L equal to 2, which means double layer. Now, here number of slots S, these variables are very important. Please understand this variable because next time when I'm going to do the winding, number of slots represented by S, here the count is 16. Layers L over here, in this case 1. Number of coils, this is very important. Number of coils over here represented by C over here, and this C is in this case 8. Now, sorry, this one in my hand, as I just told you, has 12 slots. Now if it was a single layer winding, it would have 6 coils. But if it's a double layer winding, it will have now 12 coils. I'm again repeating. This machine in my hand is a 12 slot machine, and each slot there are 2 coil ends coming up. So this means each slot is being visited twice. So instead of a single layer winding, it's a double layer winding. So there are going to be 12 coils inside this machine. If it was a single layer, then C would have been 6 over here. In my case over here, this diagram which is in front of you, here I am talking about a single layer, and that single layer has 8 coils over there. Now, if you see in this winding over here, this machine is in front of you, you have number of coils equal to 8, you know the number of layers equal to 1, you know the number of slots also over there. Can you tell me, if I tell you, okay, each slot has the number of turns per coil equal to 10. Now what is this 10? This 10 means that when you are starting from 1 and going up till 9, you will repeat 1 to 9 10 times. You will repeat from 1 to 9 10 times. You will bring the loop and then end it. Now listen this carefully, the question. Each slot is being visited 10 times, which means 10 turns per coil. You know the number of coils are 8. Can you tell me how many conductors are there in the machine? I'm repeating the question. There are 16 slots, 8 coils. It's a single layer winding. And from slot 1 to slot 9, or from slot 1 to slot 10, slot 16 to 18, 11 to 3, 12 to 4, 13 to, it would have been 5th, on this one. 1 to 9, and similarly this would be, actually मैं गलत कर रहा हूँ, 2 to 10, 1 to 9, 3 to 11, 4 to 12, 13 to 5, 14 to 16, 15 to over here 16, 16 to 8. These are 8 coils. ठीक है जी. हर coil के अंदर 10 number of turns है. Can you tell me how many conductors are there in your machine? हर coil के अंदर आपने 10 दफ़ा उसको फेरा दिया. There are 8 coils, not 80. One coil has 2 conductors if the number of turns are there. Why 2 conductors? If I go back on your first diagram, इस first diagram में क्या हो रहा था? Starting from A up till B it was 1 conductor. B to C कुछ नहीं कर रहा, ना EMF produce करता है ना force. But from C to D this is one other conductor. So one loop has 2 conductors. One loop has 2 conductors. So if I go back on this diagram over here, in this diagram you have 8 coils. Number of turns, let me write down this value. So the number of turns comes out to be 10 turns. NC is the number of turns per coil. So C is 8. 8 multiplied by 10 multiplied by 2, 160 conductors. And 160 means that if every conductor is going to produce a force equal to ILB, ये एक कंडक्टर पे फोर्स है ना, तो द होल मशीन इज गोइंग टू प्रोड्यूस 160 multiplied by ILB. So I hope you can see where this is going. I started it from a single loop. Now there are 8 coils inside your machine, which is a single layer winding. It has 10 turns per coil. So they are 160 conductors. 160 multiplied by ILB. This is the total amount of force. And you can just multiply it by R, and that will be the total torque of your machine. So what this means, if I go back on this diagram, one formula which is coming up your way now, that if you want to find out the total number of conductors, Z, total number of conductors in your machine, Z is equal to 2, the same 2 which is coming up for one coil, there are 2 conductors, multiplied by the number of coils, multiplied by the number of turns per coil. Now I have given you a diagram over here. I have shown 21 number of turns per coil. Okay? What I am doing over here in this diagram, if I go back over here, I am only showing a cross over here like this and like this. But what this cross means, that there are actually 21 or 20 or whatever number of turns, and all of them have a cross inside it. So instead of putting 21 or 20 crosses, the easy way around is I only put one cross, because all the conductor, and I tell, okay, what is NC over there. So this formula tells us the number of conductors 2C and C. Now this formula, even if you have a double layer winding, now let's go to the case if you have 16 slots, and here now I make L equal to 2. Now what happens, this time now the number of coils will become now 16. So if you go back on this formula, 2 multiplied by 16 multiplied by NC. NC can be 10, NC can be whatever value. It can be 21 or whatever. So then you can find out the total number. So you can see more the number of layers, more is the torque produced or even EMF produced over there. So this Z is very important, giving you the total number of conductors on which either if you are working as a motor, the force is going to be exerted. If it's a EMF or generator something, then more EMF is going to come out. But in case of EMF, there is going to be a slight problem over there. Why problem? Because you have, like, supposingly in this machine 160 conductors in your machine. Now each of those conductors have an EMF VBL. Now all of those 160 conductors, if they are connected in series, then you will get an output 160 multiplied by VBL. But out of those 160, they are arranged in such a way that 80 are in series, and then the next 80 are in parallel. Your voltage will be reduced because the only 80 are in series. There are two paths now. So I am looking something at this diagram. Now see this one very carefully. What I have done, same diagram, nothing changed over there. See this diagram. I have slot number 1. And here coil number 1 is there from slot number 1 to slot number 9. Then I have from 2 to 10. Then I have from 3 to 11. Then I have 4 to 12. Then 5 to 13. 14 to 6. 15 to this one, and like this. Layer 1, 8 coils over there. Now those 8 coils are going to be connected in series or parallel. So if you see very closely now, if I am starting from 1, I have started my winding from 1. I go to 9, do many number of turns, whatever I required, maybe 10, maybe 20. And then when I have completed the coil from 1 to 9 slot over there, then this yellow color connection tells me that I am going towards slot number 7 from the forward. From the front of this one rotor, I have completed from slot number 1 to slot number 9. And then from here I go to 7. And then from 7 to 15, repeat it like 10 times or whatever the number of turns per coil, and then from the back of this coil I am going to connect it with 13, and then from 13 to 5 I am going to complete it again 10 times or whatever number of times, and then from the front I will complete it with slot number 3, and then from 3 to 11 again I will do those 10-20 times whatever that number of turns per coil, and then from this 11 I will join this one with slot number 1. Now you may have a question now that this winding is now started from 1, ended at 1. So this is a short circuit. but it's not. Why? Listen this carefully. This rotor over here is actually rotating. To give current to a rotating thing, you are using those carbon brushes or commutators over there. Now, what you have started a winding from 1 and ended at 1. So, when this is rotating, maybe slot number 1 is in contact with the positive carbon brush and slot number 9 or slot number maybe 5 or whatever, that is in contact. So, when this winding is going to be in front of you, maybe at some time you started from coil 5, coil 3, coil 7 and coil 1. So, these are the carbon brush positive and negative. So, what is happening? 4 coils are in series. The rest of the 4 coils are here in series, making 2 paths over there. Now, if the machine now rotates, what will happen? Coil number 1 will come over here and coil number 5 will go upward. So, this is a closed winding. Current will still go inside, but this time coil number 1 was here in front of the negative pole. Now, it will move here, coil 5 will over there. So, when the machine is rotating, all of these windings are also rotating over there. So, their contact with the positive carbon brush and the negative carbon brush, but keeping, since they are all in series, same current is going to flow with everyone. So, now in this diagram, I have only shown one path. I started from 1, ended at 9, then I did this one, then I started from 15, I started from 15 and completed over there, then from the back end to 13, then from 13 to 5, completed it, went to 11 and then completed this one. The remaining slots kaun si reh gayi hain? This one, this one, this one, this one, this one, this one and this one over here. How many are there? 8 over there. This will constitute the next path. In this machine now, how many parallel paths are there? 2. And this is called as A variable, which is A equal to 2 over there. So, in this machine, what you are getting, if you had 8 coils, 4 coils are in series, 2 paths in parallel. So, supposingly, if one of your coil was producing 10 volts, for example, you are going to get on the output here 40 volts as an output. And if each path was capable of producing 10 ampere, for example, now you have a machine which has 40 volts into 20 amperes coming out. Now, see this diagram which is just below. Now, over here what I have done, I have connected all the coil in series. So, now all the 8 coils are now in series, and if you see this diagram, each one of them is producing 10, 10, 10, 10, 10, 10. So, what is the output voltage? 80. And the output current 10 amperes. So, the connection of your coils in series or parallel actually tells you that what value of voltage and current you are going to get from your machine. Here the number of parallel paths is 1. In this diagram, this is equal to 2 over there. So, now this is still not a very verified diagram of winding. We'll do this next time. But just trying to tell you that in any machine, number of parallel paths is a very important factor, telling you that your machine, if supposingly this is a motor, आप इस machine के अंदर supposingly 10 ampere current enter कर रहे हो, ठीक है? You have a 10 ampere current entering this machine. So what will happen? 5 ampere will flow here, 5 ampere will flow over there. So when you are trying to find out the torque from that machine, 5 ampere in this, 5 ampere in this, and you can find out your torque. So this one is telling you the number of parallel paths here 2, here this is equal to 1. Now, very, very important thing, see this diagram. What is happening over here? Here I have, instead of 2 poles, I have 4 poles over here. Now in this 4 poles, remember one thing very carefully, whenever you are having more than 2 poles, every pole has to come after the opposite pole, which means that if there is a north here, the next pole should be south. Never put a north here, because this north and north, it's just one pole. So when it is a north, please put south, and then afterwards put a north and then south. So this is a 4-pole machine. If you wanted to make a 6-pole machine, then there will be 6 poles, north, south, north, south, north, south. Now, in this machine, assume this is a generator. Again, I have those 16 slots or whatever, and there are some coils over there. They are in series or parallel. I'm not concerned with that because I'm not concerned with their value of current and voltage. The thing I am concerned about is this, that when it is in front of the north pole, supposingly, I am going to supposingly get a cross over there. Maybe this is cross. Let me remove this one. And when I'm in front of the south pole, this will be dot. And when I'm in front of the north pole, this will be cross. And then in front of the south pole, it will be dot. But since all of these windings, they are in series, I will be getting some voltage output over there. But when this whole of your machine is going to complete 360 degrees of the revolution, the waveform you are going to get as an output, this time it's going to be two waveforms over here like this. I'm again repeating, it's a 4-pole machine. When you are going to complete whole one revolution, which means 360 degree of revolution, the output waveform is going to be 2 cycles. Okay? Here in your diagram, if I go back to this diagram where I discussed this one, what was happening? I asked you or told you that this loop completed one complete revolution. So what you got? You got this waveform, up till this point. Now you have 4 poles. So whenever you are crossing a pole, you are going to have a transition from positive to negative. Or similarly, even if you have north-south poles like this time if you have 4 poles, then you will get something. This is 1, this is 2nd. So you will be getting 2 cycles. So what I mean by this, if I go back on that diagram again, now there are 4 poles. And how many are cycles I am getting? This is 2 cycles, which means that I am getting 720 degrees of the electrical waveform. आप जब कभी भी electrical waveform sinusoidal को देखते हो, one complete cycle 360 degrees. You have 2 cycles now, 720 degrees. So now here the very important thing, you completed your total revolution that was 360 degrees. And certainly it was mechanical in nature because you completed one in space. So this is theta m, mechanical angle. But if you had 4 poles, you were getting approximately 720 electrical angle. So what this means, that your mechanical angle was 360 degrees, but electrically you got 720 degrees. Okay? So what this means, that theta electrical is equal to 2 times your theta mechanical. Now, if you want to make it a journal formula, what is this 2 telling you? This 2 is coming because there are 4 poles over there. So if I change this one to theta electrical equal to P by 2 theta mechanical. What this means now? I have 4 number of poles, 4 divided by 2, 2. So this means over here, your theta electrical is 2 times your theta mechanical. For example, let me make a small diagram over here. And in this diagram, if I make this is my rotor. And over here, if I make a small diagram, it's a little difficult to draw 6 poles, but still I will try. North pole, south pole, then another north pole. Not effectively very good, but still anyway, I'm trying to make it 6 poles. This is again north pole. South pole. Now here in this machine, if you are going to put a conductor, supposedly at this point and this point, and you complete one complete revolution over here, okay, this time the output waveform you are going to get is going to be, this is 1 cycle, this is 2 cycle, and you will get 3 cycles. I don't have space actually. So this means this time you have completed for theta mechanical, you completed 360 degrees. Theta electrical is going to be equal to 180 degree multiplied by. Now whenever you are coming from north pole to south pole, this is 180 degree. Then from south to north, another 180 degree. Then from north to south, another 180. Then from south to north again. So how many they are going to be? This time they are going to be 6 times over there because there are 6 poles. So you are going to this time, the formula is theta electrical is equal to P by 2 theta mechanical. This time your number of poles are 6. So 6 divided by, so your theta electrical is 3 times your mechanical angle. So this time your electrical angle is 3 multiplied by 360 degrees over here. Fine. Ji, any questions with this, Ji? नहीं, आप इस मशीन को अगर देखो, देर आर 2 सेट ऑफ कॉइल्स. मेरे पास अगर ये मशीन है, आई हैव दिस मशीन ओवर हेयर, फ्रॉम स्लॉट 1 टू स्लॉट 6 दिस वाज 1, देन फ्रॉम स्लॉट 1 टू 12 अनदर 1. अब 1 से 6 तक जो गई है उसको मैंने 12 दफ़ा 20 दफ़ा जितनी मर्तबा भी किया है, दैट इज़ द नंबर ऑफ टर्न्स. ठीक है, लेकिन स्लॉट 1 से एक 12 की तरफ भी जा रही है. दिस इज टेलिंग मी कि एक स्लॉट के अंदर अब 2 कॉइल्स हैं. दैट इज, अब मैं 3 भी रख सकता हूँ, दैट विल एल विल बी 3. तो इसका मतलब ये कि अगर मेरे पास 16 स्लॉट्स हैं, नंबर ऑफ लेयर्स 2 हैं, तो आई विल बी गेटिंग 16 कॉइल्स. अगर 3 होते देन आई विल बी गेटिंग 24 कॉइल्स. More the number of layers, more are the number of coils inside it. Practically, in simple machines, L is always 1. But if you want to increase the output of your machine, your L will be either 2, 3 is rarely possible. Rarely they do it because for 3 coils, you will have more space to be created. More space means more reluctances and all those problems. So, 2 or either 1, they are the most commonly used over there. So, number of layers here represented by 1. And here if you have 2 coils per slot, then this means L is equal to 2. Yes, complicated. Of course complicated. I have still not talked about the winding stuff over there, because inside your winding you have why this is not getting. So I have not still talked about the winding. These 2 diagrams I have shown you just to tell you that what are parallel paths. Practically in the next lecture I will talk about the windings. There are 2 types of winding inside a DC machine. One is called as lap, the other one is called as wave. We will discuss them in very much detail. Okay, any other questions?